Hi everybody, this is Mr. Folly, and I apologize again. I always shows back to my screen to what apparently is my favorite daughter. This is the second time going through for this, so I apologize for that. First one didn't record the screen, so that was kind of a bad news thing. But as you all know by now, I hope, this is Mr. Folly, and let's talk a little bit about Lewis dot structures and shapes. So, steps on how to draw a Lewis dot structure. This is going to be a lot when you read it, and then we'll do examples and it'll make more sense. So, how do you do it? You're going to be given a structure X. You're going to be given a structure like XA, XA3. Okay, so put the least frequently occurring atom in the middle. Oh, that would be X. So there's only one X and three A's. Add the other elements around it evenly. Add valence electrons, and remember your periodic table tells you the valence electrons you have. 1, 2, 3, 4, 5, 6, 7, 8. Now, I do want to emphasize that Lewis dot structures are for covalently bonded substances, so they're typically two or more nonmetals. I have some semi-metals in there, please forgive, but that's it. All right. Once you add the valence electrons, you sing a song, connect the dots, la, 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 and then it's there. Negative ion. So if it's a negative ion, you add electrons anywhere. And I'm going to add this bracket, so remember to put a bracket around it. Positive ions. Remove electrons from anywhere. You can move electrons however you like. You are the master of the electrons. So that means you can pick them up and put them somewhere else. You can make single bonds, double bonds, all those other things. Rules. Rings are wrong. So you will never have no triangles, okay? The central atom likes to have 8, but can be higher, the third period or below. So that means that oxygen can never have more than 8. That's row 1, row 2, period 3. Sulfur can, phosphorus can, chlorine can, but fluorine can't. Okay? The outer atoms must have 8, but don't forget our friend hydrogen. He needs to be full. 8 really isn't that magical a number, but really we're looking to be full, not 8. Okay? Can form chains of carbons or acids. Acids are much later, so now we're only talking about chains of carbons. So let's do some examples. All right, so let's start with my old friend CH4. Carbon goes in the middle, and from the periodic table, I know it has 4 dots. Then I have 4 hydrogens, and notice how I aim my hydrogens at my single electrons. Single electrons form bonds, so what I like about this method, which is a little different than what other people do, is it emphasizes the single electrons form bonds part. So now I've got all my valence electrons, and I sing, connect the dots, la, 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 connect the dots, la, la. That's it. If you've done it a different way, we have to count and recount electrons and all that. Our electrons are in there correctly because we used our valence, and that's it. C2H2. I like this because it's got 2 carbons. Carbons form chains. So I'm going to do my carbon. I'm going to make it a chain right next to each other. And then remember, symmetry is beauty. Oh, isn't that cute? So I'm going to try and keep these symmetrical, okay? So carbon has 4, hydrogen has 1. Connect the dots, la, la, la. Ooh. So now what I want to do is I want to connect these 2 and these 2. So what I'm going to do is just connect them, but I'm going to make it look a little prettier, okay? Prettier than your handwriting right now, Mr. Folly? Prettier than my handwriting right now. And that's a triple bond. All right, first one's got a charge, OH negative. Oh my goodness. 1, 2, 3, 4, 5, 6. I'm going to aim my hydrogen and its single electron at another single electron. Connect the dots, la, la, la. Oh no, I have a single electron. Single electrons are evil. That's never allowed. But we have a gift here. My gift is the negative electron. So that means I get to add this bonus one. I'll make it big. And then to remind you that it's negative, I'll put it in brackets with a negative sign. Oh, I see now. Okay, what if it's positive? I'm going to take away an electron. Let's see how that works. Nitrogen goes in the middle. 1, 2, 3, 4, 5. Balance them out. It doesn't matter where you put the pair. I've got 4 H's. Spread it out just like CH4. Every H has a single electron. I'm aiming my singles at each other. Now here comes something you're not going to like. Okay, first part. Connect the dots, la, la, la. I can split up a pair, okay? Pairs tend to be pretty stable, but they can be split up, and we're going to split it up here. But notice I have that single electron again. But it's positive. Positive means I can erase anyone that I want. You will die. And it's gone. It's got a charge, so I'll put it in a bracket. Ba-bam. All right, SF6. Ooh. S has 6 electrons. Quick refresher. How did I get 6? Number of valence electrons comes from the periodic table. Okay. I have 6 fluorines. Okay, this gets kind of tricky. I know I do up, down, left, and right. But the other ones, I got to put them somewhere. So I guess I'll put one top right and one bottom left. And then each fluorine has 7. I'm going to aim my single electrons at sulfur, so it'll bond. Still adding electrons, 7 for each one from the periodic table, and I'm connecting the dots. Connect the dots. Remember, I can break pairs. La, la, la. Oh, no. Okay, this one. Oh, I missed. That's kind of embarrassing, man. Hand-eye coordination is leaving me. This guy right here has a single, but I've got this one over here. If I draw it like this, somebody should smack me in the mouth. Ow! Ouch! So that just looks too ugly. Remember, there is beauty in Lewis dot structure, so let's make it beautimous. There you go. All right? 6 bonds. Why can sulfur do this? I thought it has to have 8. Sulfur's on that 3rd row. Sulfur could do it. Okay? XeF4, just kind of as a little note, here's xenon. It's a noble gas, so you'd think it wouldn't bond, but guess what? AP Chemistry says it does, so we're going to do it. It is down low, so we can also break the octet rule. Speaking of octet, xenon has 8 electrons. And throwing out some fluorines. Throwing out some Fs. Oh, you're a mean chemistry teacher. I don't throw out too many Fs. Or I suppose I throw them out. I don't keep them. This is a retake one. Get it? Because of all the Fs. Connect the dots. La, la, la. Connect the dots. We're good with splitting up our pairs now. But now I have 4 single electrons. Ugh. For half a second, you might consider double bonding. If you double bond it, first of all, it doesn't do anything because I still have a single electron on the fluorine. So that's not going to be any good. And that would give fluorine 2, let me see if I can hide it. That would give fluorine 2, 4, 6, 8, 10, right? And fluorine's an outer atom, and the outer atoms cannot have more than 8. So we're gonna drop that. So what I'm gonna do is I'm gonna pick up my 4 singles, and let's see here, this is like 2nd grade math once you hear it. 4 singles turn into 2 pairs. Oh no, turn into 2 pairs. 1 pair, 2 pairs, and something didn't erase, so I went through it. Okay, there you go. All right, formal charge. Formal charge for each element. Bum, bum, bum. Valence electrons from the periodic table, right? So we're using that a lot. Minus electrons in pairs, minus half the electrons in bonds. So if I have a single electron, you get 1 electron. If I have a double bond, I said a single electron, I meant a single bond. This would be 2 electrons. Okay? It's hard to say in words that everybody gets the same thing, but hopefully that'll make sense. Formal charge for an entire particle equals the charge on the entire particle. So that means like this thing right here. See how geez. Hydroxide has a -1 charge. That means the overall formal charge is going to be -1. So let's do that one, okay? So if I did oxygen, oxygen has 6 valence electrons, periodic table, minus, what is it again? Number of electrons in pairs, 2, 4, 6. 6 minus 6 minus the bonds. It's got 1 bond. Minus 1 equals -1. So oxygen is -1. Hydrogen. Valence electrons for hydrogen is 1. No lone pairs, but I've got half of the ones in the bond equals 0. Well, if I add -1 and 0, I get -1. Oops, I get -1, and I'm a winner. Okay? This is a key thing. Lowest formal charge is preferred. That is 0. Zero formal charge is seen when every single electron forms a bond. NH3, remember N looked like this. A quick eyeball thing. See how this has 3 single electrons? If nitrogen has 3 bonds, its formal charge is 0. Okay. The other thing I wanted to say, what's my other formal charts thing I was going to say? Oh, the most electronegative atom gets the negative formal charge. Okay, so if you're trying to decide which one will work, oxygen's very electronegative. It's very often -1 or -2 from there. All right, AP asks for the best structure based on formal charge, which means that we are going to use these things to identify. Octet rule. All atoms have 8 valence electrons when a molecule is written. Double and triple bonds are okay. No 5 or 6 bonded atoms. So notice how sulfur right here breaks the octet rule because it has 1, 2, 3, 4, 5, 6 bonds. 6 times 2 is 12. So SF6 breaks it. So that means that is a bad based on the octet rule. Okay. And just remember, hydrogen is going to be 2. So whenever we talk about the octet rule, it's everybody wants 8 except for hydrogen. Hydrogen has to have 2. All right, let's talk about resonance. Sometimes a Lewis dot structure is made where a double bond could be between 2 different atoms of the same type. So I'm looking at this guy right here to see how the double bond could be the top, the left, or the right. But I could have just as easily have written it where the double bond is to the right. Or I could have just as easily written it where the double bond is to the left. So sometimes a Lewis dot structure is made where a double bond could be between 2 different atoms of the same type, 2 or more. This moving double bond is called a resonance structure. Okay, it doesn't move, by the way. It's an average. It's called resonance because they thought it was moving and would bounce back and forth, which would resonate like a beautiful note. La. Resonance improves stability. The more resonance structures are favored over less or none. More resonance. So do you see how this has 3 resonance structures? That would be more favored than something that has 1 or none. Resonance structures spread out the negativity of the double bond with 4 electrons close together. So remember, this is an average. So the electrons aren't concentrated here, concentrated here, concentrated here. They kind of zhuzh over all of it. Okay? So whenever you have a double bond, you should check for resonance structures. So let's just do one and go, check out the resonance. Carbon has 4 valence. Doink. 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 Now I have this single electron, which is going to form a double bond with one of them. It depends on which one that we want to do. So I'll double bond to this guy. Okay. Now I want to remind you that this gets kind of ugly because it's -2. So I have a bonus electron and another bonus electron. So there's 2 ways to draw this. You see the one where I draw it 3 times. This is -2. The other way to draw it is to see OOO, and then you put a dashed line on all of them to represent that they're all kind of bonded in a halvesies. And that's it. Welcome to the end of resonance structures. I know you want to look at the shapes, but we'll have to do that next time. And for that, I will say toodles.